Hello everyone! In today's lecture, I will be giving an introduction into the basic statistics for psychology and neuroscience. However, before I begin, I should point out that I myself am not a statistician. I'm just a neuroscientist. So when I'm explaining these kind of things, I won't be going into the full detail of how to calculate certain statistical values. I mean, I will give examples of that, but I will more take an approach of how you should interpret these kind of things when you are reading a paper and how to understand what a paper means when they are reporting statistics, just for you to make it easier to read the results section. So I might screw up some terms. I may say things that are, for a statistician, not fully perfect in the way that I explain them. For me, it's more important that I convey a certain kind of understanding of statistics, how you would apply this in psychology and neuroscience. All right, so with that, let's get started. So, in psychology and neuroscience, if you want to do statistics or if you want to know something about the brain or human behavior, you first got to have some data. And data we get typically from participants, although we also could get it from a computer simulation. Anyway, we get the data from one participant, for example, the performance on a reaction time task, or how well somebody did on an IQ test, you name it. Now, this data of one participant is obviously not enough to make a conclusion about an entire population. So if we want to make a conclusion about an entire population, we have to get them more data, with more data points to make our conclusion. Obviously, the more data we have, the better we can represent that population. However, of course, we are limited in our resources, time and money. Now, when we gather that data, what we can do is we can represent this. We can represent this in a figure. Now, putting all our data into a so-called histogram, which is a distribution as shown here, gives you an idea of where everybody scored. So in this case, you will see that most people scored somewhere in the middle, let's say 100. I don't have any numbers on the x-axis, but just imagine it. In the middle, there is 100. The highest bar there means that most people there scored around 100. Whereas there are a few people that scored very, very high, let's say 200, and just a few people scored very, very low, which might be 0 or 10. Now, of course, your distribution of your sample, which is called a sample distribution, can also look different, of course. For example, you could have, it could be the case that a lot of people score very low, let's say around 50, and there are just a few people who will score very, very high, let's say 500. Then it means that most people will be on the lower end and just some people will be on the higher end. Then you get a distribution that is a little bit skewed. In this case, it's skewed to the right, because the tail of the distribution is basically to the right. This is a rightward skewed distribution, or a positively skewed distribution. Of course, you can also have the opposite, where a distribution is skewed to the left or negatively skewed, where people mostly score very, very high, but there are just some people that score very, very low. Now, when doing statistics, we will be working with those kind of distributions, particularly the one in the middle that looks very symmetrical. We will get into this in a minute, but before I do that, it's good to define some terms. Terms that I will be using throughout this lecture, so these are very important. Now, there is something called the dependent variable. And the dependent variable, that is the thing you measure. So, for example, I give already the example, we could measure a reaction time or somebody's average score on a test, an IQ test or something like that. That thing that you measure, in this case reaction time or IQ test, is is called a dependent variable. That's the thing you measure. That's where you get your numbers from. Now, between brackets, I wrote that this variable is often continuous. What does that mean? A variable is continuous if it consists of a whole range of numbers. For example, IQ score can go from whatever 0 to 200 with an average around 100. Or reaction time can be as low as 200 milliseconds, but can also go up to multiple seconds, right? So basically every number is unique. You have a whole range of numbers, and that's what we mean with a continuous variable. Now, a thing that you measure, a dependent variable, could also be not continuous, and then we call it categorical. It could be not a range of numbers, but just 2 categories or 3 categories. Imagine, for example, that we would look at voting behavior in the United States. If we take a sample and look who voted what in the United States, there can be only 2 options, Republican or Democrat. Well, I guess there could be more options with independents, but let's just say we have Republican and Democrat. Then in that case, your dependent variable is categorical. The thing you measure is expressed in categories. Now, in a lot of experiments in psychology and neuroscience, the dependent variable is continuous. There might be examples where it is categorical, and there is a whole range of statistics where we can look at categorical dependent variables. But in today's lecture, I will be only covering statistics for continuous variables, because that's what we look at most of the time. Reaction time, accuracy, brain activity in a certain region measured by fMRI, brain oscillation activity measured by EEG. Those are all continuous variables, and that's what I will be talking about mostly today. Now, another thing is the independent variable, and the independent variable is the thing you manipulate. So what do I mean with that? For example, if you're comparing 2 groups with each other, let's say a group that gets a placebo medication versus a group that gets a real medication, then you would want to know how those 2 differ on the thing you measure, right? Let's say we'll measure again reaction time. You would want to see how those 2 groups, placebo group, real group, differ on that dependent variable. This is your manipulation. Some people get the placebo, some people get the real thing. And that is what we call the independent variable. Now, in this case, again, I have 2 categories, right? So placebo, not placebo. So that would be an example of a categorical independent variable, because my independent variable can be separated into categories. Here on the slide I wrote down discrete. Discrete is the same thing as categorical. But of course, our independent variable can also be continuous. For example, we could look at the relationship between height and IQ score. Now, I don't think that we would find any significant findings there, but in this case you would look at, okay, if height changes, does also your IQ change? And if that is the case, then we have a continuous independent variable, the thing we're looking for, whether it has an effect on the thing we measure. In this case, height would be continuous. And I will be giving examples in the statistics today about both continuous and discrete or categorical independent variables. All right, so let's continue. Before we do any statistics, we have to define 2 hypotheses. That's first of all the null hypothesis and the alternative hypothesis. So the null hypothesis, that is your starting point. So for example, let's come back to the example with the 2 groups, a placebo group and a real medication group. Then your starting point is that there is no difference. The starting point is always that you start when there is no deviation, or you expect no deviation from the start. So for example, a null hypothesis about that would be the real medication group doesn't score any higher than the placebo group. Or height has no effect on IQ score. That would be another example of a null hypothesis. Now the alternative hypothesis is a result that deviates from that starting point. And that's typically what we're after. So it's a little bit interesting that the null hypothesis, our starting point, is not the real thing we're after. We're basically after the alternative hypothesis. And those are the results that deviate from your starting point. So, for example, a finding that is smaller or larger than an expected value, or smaller or large, or that one group is smaller or larger than the other. For example, the medication group scores higher than the placebo group, or height does have an effect on IQ. That would be a alternative hypothesis. Now, why do we formulate it like this? Why is our starting point no difference, and why is the thing we're looking for, the thing we're after, the alternative hypothesis, why is that the one? Why is it not the opposite way? Well, it's kind of the same thing as in court. A defendant is non-guilty or is not guilty until proven otherwise, because if you would have your because otherwise you would have to prove that somebody's innocent, and proving innocence is almost impossible. It's the same with statistics in science. You cannot prove negative, or it's very, very hard to prove negative, because you have to rule out all other possibilities. Whereas if you turn it around, then you're just looking for that one thing that you're after. So that's why we formulate the null hypothesis to be no difference, and the alternative hypothesis to be the thing we're after, rather than the other way around. All right, so let's come back to this distribution of our scores, the so-called sample distribution. Now, the sample distribution, as shown here on the left, I already said that those bars represent the scores of different people. So it's basically the quantity of a certain score. So for example, every bar is a range of, let's stay with reaction time, of 10 seconds or 10 milliseconds. Then there would be just a few people who score between 0 and 10, still only a few between 10 and 20, and then you can go on like that, and then most people score somewhere between 100 and 110. A lot of people still score between 120 and 130, and then just a very few people score between 200 and 210. So that's what those bars represent. And each individual score of an individual participant is basically then represented in this histogram. Now, when writing down statistics, we of course have to define some ways to mark that. And in this case, every observation is x. And then in this case, you will see that here there is this xi, and I just stands for the number of the participants. So every score of each participant is represented in this histogram. So x1 would be, for example, here, x2 would be here, x3 would be here, and then x4, x5, and so on. And then here we would be at x110, x111, and so on. So every score is called x1 to whatever. So x, and then we represent it as xi. Now, when you see a bar above the x without the I or number behind it, then that's our mean, that's our average of all the scores. So one other thing that we have to define when we're looking at this sample is how broad is it, right? It could be that the scores range from extremely small to extremely large, or it could be that most people score very closely to each other. For example, everybody scores between 100 and 110. So then in that case, this distribution would be very sharp. Whereas if some people score 0 and other people score 3,000, then that distribution would be a lot broader, right? And this is we can represent with the standard deviation. Now, what the standard deviation is and how we can calculate it, I will come back to in a minute. Now, you will say, okay, now we have this distribution, and we can of course calculate a mean, how to calculate an average of something, which is something which we learned in school, so that shouldn't be a big problem. Standard deviation, I will talk about it in a little bit. But why would this be important? Well, we can represent, this sample can be represented as a normal distribution. And a normal distribution is something which you see here on this slide on the right. A normal distribution is basically a perfect shaped function that follows certain characteristics. It's called the normal distribution. It's sometimes also called the Gaussian distribution. Now, this normal distribution has certain properties, and it's those properties that we use in our statistics. So this normal distribution is very, very important. And that's why I also in the beginning said that, okay, you can have these sample distributions, from your data that can be skewed to the left or to the right, and that can be problematic when doing statistics. I will be going to this in even more detail later on, but for now, just note that it is very, very good to have a distribution that is symmetrically shaped, as is here on the left, and whereas a skewed distribution is problematic if we want to use this normal distribution here on the right. So basically what I'm saying is that on the left, that's the thing we have measured. We have done our experiment and we got data from that. And on the right, that's a function, that's a mathematical function that we use to represent the thing on the left. So on the right, that's just a more theoretical approach of what we have actually observed on the left. And we use this theoretical approach on the right to do the statistics with. So if the thing on the right, the normal distribution, doesn't look like the thing on the left, then you cannot do the same statistics with this normal distribution. All right, that was quite a mouthful, but okay. Let's come back to this normal distribution. So as I said, this normal distribution has certain properties. The first property is that it's symmetrical, and that's cool because then it means the average or the mean is in the middle. And it means that there is an equal amount of data to the right and an equal amount of data to the left, i.e. it's not skewed. Another thing we know about this normal distribution is that if you go a certain step to the right or a certain step to the left, then a certain percentage of observations will fall into that range. And with that we come back to this standard deviation. So when we're going one standard deviation to the left, between the mean and that one standard deviation to the left from the mean, there's 34.13% of all data that we observed, if we would represent this by this normal distribution. If you go one standard deviation to the right, again 34% of data will be represented there because of course it's a symmetrical distribution. Now, why is this a good thing? Because then we know if we would look at some point in this distribution, right, we would just put a dot somewhere on this distribution, we exactly know how many observations we would expect there if our distribution would follow this normal distribution. And that's quite cool. So for example, if you would quickly sum it up, you would see that 2 standard deviations to the left and 2 standard deviations to the right, if you would take that entire area between minus 2 standard deviations and plus 2 standard deviations, if you would sum that up, 13.5 plus 34 plus 34 plus 13.5, that's 95%. So we know, or approximately 95%. So we know that approximately 95% of observations from our sample will fall between 2 standard deviations to the left and 2 standard deviations to the right. Why this is all important we will come back to in a minute, but it already shows you that if we have a sample, like on the left, that we can represent by this normal distribution on the right, then we know where our data is and where our data, or how much of our data is represented at what point. So how do you calculate the standard deviation? So the standard deviation is basically let me come back to one other thing first. So I said on the left, and the mean is represented by this x bar, and a standard deviation we call s. Now when you look at the right, this normal distribution, you will see different symbols, right? You see this mu, which is the Greek letter m, or the Greek equivalent of m, and you see this O, this round shape, which is a sigma, and this sigma is the Greek synonym or the Greek equivalent for s. So in this case, the mean is mu, and the sigma is standard deviation. So why do we give it another symbol than on the left? Well, with that you can distribute, or you can distinguish between the sample distribution that you like, the sample distribution that from your data. So the left is actual data, with x bar being the mean of the actual data, and s being the standard deviation of the actual data, whereas mu and sigma represent this normal distribution, which is this theoretical approach to the thing. So if we do statistics with normal distribution, we would be talking about mu and sigma. But yeah, just remember that the mu and sigma basically are a theoretical approach, whereas x bar and s are what you actually observe. So if you read a mean in a paper, then that would technically be x bar, whereas mu and sigma are the ones you do statistics with. Anyway, it doesn't really matter, just remember that either x bar or mu is the mean, and s or sigma is the standard deviation. You can, if you use them interchangeably, that's not, nobody's going to be mad. Well, except maybe some statisticians, but it's not that important. Anyway, so what's the standard deviation? So the standard deviation, sigma in this case, or s, is a certain observation minus the average squared, and you take this difference between the your observed score and the mean. You sum that up for all observations. So if we go back to our sample, let's take that the first observation was a score of 2, and the average is 98. So then you would have 2 minus 98 is minus 96. You take the square of that. Then you sum up the next one, plus, and then the next score would probably, or might be 4. Then 4 minus 98, 94 squared, plus next score, 6, and so on. You do this for all of them, and then you divide this by the number of observations that you have, and then you take the square root of that. That's how you calculate the standard deviation. You can actually do this by hand relatively easy if you practice it a few times. Now it may seem a little bit complex, but you can calculate it relatively easily. And as I said, the cool thing is, if you have this standard deviation, you exactly know how far a certain observation is away. So for example, we could also represent, or we could, for example, say in our sample distribution, if we know that a certain observation is 2 standard deviations plus the mean, then we know that this is somewhere around the 97.5% observation. Now, you would say, okay, why is that important? Well, we come back to that in a minute. Now, one important thing, before I ramble on too much, is that when we want to do statistics with this normal distribution, then of course our sample distribution on the left needs to be normal, right? It needs to be, and with normal we mean this symmetrical bell-shaped form. It shouldn't be a square, it shouldn't be skewed, it should be approximately looking like this. I mean, it will never be perfect, but the closer it gets, the better it is. If you don't have that, then you get a problem when you want to use statistics with this normal distribution. And all the statistics I will be talking about today, mostly all of them, will use this normal distribution. So that shows you why this is so important. Anyway, let's move on. Now we talked about the sample distribution. And then I said, okay, in the sample distribution you have certain observations, participant number X who scores a certain point, participant X2 who scores a certain point. Now when we want to do statistics, we typically don't compare if one participant had a larger score than another participant, right? What we want to do is if a certain mean is larger than another mean. What do I mean? So coming back to my example, we would, for example, want to know if the group who had a real medication, if they scored higher than the group who got a placebo medication, which means you have all the people who had placebo on average score lower than all the people who got a real medication. Which means we're not looking at a single value of a single participant, but we want to look at whether a certain average of a distribution is different from another average of a distribution. Now the principles are all quite similar, except that we now would have to look at a distribution where all those bars, all those numbers in those bars are not single participants, but they are actual means of a certain group. Now, you would say, okay, but I'm not going to do 10,000 studies or something like that. I'm just going to do one study, and I don't want to have 10,000 placebo groups and then 10,000 actual real medication groups. I want to have one group with, let's say, 100 participants. And that's why this sampling distribution, which is the distribution of different means, you can actually get this from your one sample. Now this may seem a little bit fake, but it's true, because we use this normal distribution, right? And I said already this has certain properties. So if you just have the mean and just have the standard deviation, you don't need to know how every of those observations look like. You can already get, or you can know where a certain observation is by just having the mean and the standard deviations. You don't need all individual scores. So that's why having a single mean of a single group, placebo or real medication, is enough. Now, what is then the difference between a single sample distribution and a sampling distribution? Well, the thing is that in a sampling distribution, this normal distribution, how broad it is how much it goes to the left and how much it goes to the right, is not the standard deviation, but it's called the standard error of mean. And that's almost the same thing, but the standard error of mean, which is abbreviated as SE or sometimes as SEM, that is the standard deviation which you got from your single sample divided by the square root of the number of participants within that sample. But other than that, everything else is the same. So going one standard error of mean to the left is 34%, going one standard error of mean to the right is 34%, and so on. So now, if we have our normal distribution, let's say that this particular distribution is of the group who had a placebo medication. We know what the average is of the people with a placebo medication, and we can calculate how broad this distribution is, right? So let's say the mean score on a whatever test, I don't know, let's say it's 10, right? And we know that the broadness of this distribution is 5. So when you have a mean of 10, then one standard deviation to the right would be a score of 15. And if you go 2 standard deviations to the right, that would be then 10 plus 2 times 5 is 20. Now you could compare then another group's mean to that first distribution. For example, the real medication group, let's say they had an average score of 21. Then you would know where this 21 falls compared to that placebo group's distribution, right? In this case, it would be a little bit larger than 2 standard errors of mean to the right. So by that you can calculate how likely it is that this real medication group would fall in this distribution of the placebo group. Because if that is very likely, then there's probably not too much difference between an actual medication and a placebo medication. But if the score of the real medication is not highly represented in this normal distribution of the placebo, then there might be a probable difference. And that's actually what statistics is, that we will be talking about in a few minutes. Again, you need to have a normal distribution to do these statistics. Now the good thing is, when you have a large number of samples, if your sample has a large number of participants, then your sampling distribution is approximating normality. Now this is a little bit hard to explain why this is the case, but it's the so-called central limit theorem, which states that the larger amount of observations you have in a single sample, the more normally distributed your sampling distribution is. It's a little bit complex, and for anybody who wants to learn more about this, you should definitely look it up. But for now, just trust me that this is the case. And what do I mean with a large N? Well, different statistics books will have different opinions about that. If you have a sample that is larger than 40, then you're probably very certain that you can that your normality assumption will be fine. However, when it's above 20, it's already getting more normal. But again, if you want to be safe, then the larger the better. Okay, so I already said that you can look at this distribution and then know where a certain score is, right? So in this case, this is, you can calculate a z-score, and the z-score is basically just the amount of standard deviations or standard errors of mean from the middle. So when you look at this formula down here, z is a certain observation x minus mu, which was the average, divided by the standard deviation. So for example, as I already said, let's take the average being 10, a standard deviation being 5, and then we could, for example, say, okay, somebody scored 7. Now this person would have then 7 minus 10, which is minus 3, divided by 5, which is 0.6. So this person would be 0.6 standard deviations to the left, because we end up with a minus sign. So your z-score would be minus 0.6, and this minus 0.6 is the number of standard deviations to the left. Now you will see in this formula that we used the sigma, which is the standard deviation. So this is a formula that would be used for a sample distribution. If you want to know if one person in a single sample or a single observation, where this falls in your normal distribution. Now, typically within psychology, and a lot of times also in neuroscience, we determine a certain critical value. Now, what is a critical value? A critical value is the value, if the z-score is larger than this critical value, then it is unlikely that your observation was based on chance. Now, as I already said, how large the percentages are in this distribution we can already see, right? So the critical value, if a score is larger than that, the critical value in this for z-score is 1.96. So if a score is larger than 1.96, let's say 2 to round it up. If a z-score is larger than 2, then you get in this critical zone. So what does it mean? 2, z is the amount of standard deviation. So if certain score is larger than 2 standard deviations, then that is a score that is very unlikely. How unlikely? Well, you can already see. If the z-score is positive, then it's 2.5% on the right, and if the z-score is negative, it's 2.5% on the left, because of course the critical value is also for the left part. So a z critical score could also be minus 1.96. So why do we call this critical value? Because at some point we have to say, okay, this observation is quite unlikely. There is something special with this person. And in psychology and statistics, we typically take a 5% value. And this 5% value is just the right part, is 2.5% on the right and a 2.5% on the left. So everything that is larger than 1.96 or 2 standard deviations to the right, and everything that is more than 2 standard deviations to the left, that is a very unlikely score. And if we have a certain observation, then we say, okay, this is such an unlikely score, there might be a significant difference. And that's where we come to this term that you so often read in papers. A significant difference is just a score that is very unlikely to happen. How unlikely? Well, smaller than 5% of cases. Now you would say, okay, but then there could still be a chance that you just have a normal person that is just an outlier, right? You have, for example, if you look at the distribution of height, most people are around, 170, 175, 180 centimeters. But there are people who are larger than 2 meters, 2 meters 10, 2 meters 20. Those are, those are very tall people, but they're not in any way special, right? And that's exactly the point. If we're doing statistics, we can never say for certain if a score what we say is a score is very unlikely to happen, and therefore there might be a strong difference. But it isn't necessarily the case. It could also be just an outlier. Later on, when we'll be giving more examples, this will become a little bit more clear. Now it sounds maybe a little bit fake, but okay. So what would we do if we do this not with a single participant, but with an entire group? So for example, the sampling distribution, right? For example, we would want to know if our people who got the placebo score lower than the people who got an actual medication. Now in this case, your z-score looks exactly the same, except that the formula changes a little bit, that the thing we divide by is not the standard deviation, but the standard error of mean. So in this case, for example, the mean of the placebo group was 10, and a standard deviation, a standard error of mean in this case would be 5. Then 2 standard deviations to the right, or 1.96, would be 10 plus 2 times 5 is 20. So if we then take another mean of a certain group, for example, the real medication group, and if they then score a mean of 21, then if you would take that 21 and put it into this distribution, you would see that that would be larger than 2 times the standard deviation to the right, or it would have a z-score that is larger than 2, right? So what we then would say is, okay, the score of this real or the average score of the people who got the real medication is very unlikely to be the case, or is very unlikely in the distribution of a placebo. So what we then would say is that there is a significant difference between the placebo group and the real medication group, which then would imply that the real medication does something the placebo does not. But of course, as I said, it could be just that we have a group of people within the real medication group who just score very, very high without the medication doing anything. It could be just it could be on chance, right? But we know how large that chance is. Very, very small, smaller than 2.5%, because it's larger than this critical value. And because this chance is so small, that's why we say, okay, the chances of this being just a random difference are so unlikely that we can conclude that the medication does actually something. All right. So, all right, this is cool. With this Z-score, we can do nice statistics. We can compare two groups with each other, for example. So, what's the problem? Or why not use this always? Well, actually, we do use something like this all the time, except that this Z-score is still based on this normal distribution, which, as I said, is some kind of theoretical perfect distribution, which works if you have an infinite amount of participants. Now, when we're doing experiments, we don't have an infinite amount of participants. We have a limited amount of participants because we can only test a few participants. And that's why we use a t-score. A t-score is basically almost the same thing as a z-score, except that we take into account the number of participants that we tested, so we kind of correct a little bit for that. So that means if we just have a very few number of participants, for example here in the pink line, with just the degrees of freedom represent, df stands for degrees of freedom, and that's almost the same as the number of participants. It's always number of participants minus 1. I will come back to that later, but just note that the lower the number of participants, the broader this distribution gets. Which means that this critical value, right, the number of standard deviations to the right or to the left, after which something is or has a chance of occurring of smaller than 5%, this critical value becomes larger because the distribution becomes broader, which means that this critical value also moves to the outside, because it basically moves with this distribution itself. So what this implies is if we have just a few amounts of observations, if we just test like 5 participants, then we need more evidence, or we need a larger difference to actually imply that an observation was something special, or that two groups differed from each other. So for example, with a group of 5 people, your critical value is maybe not 1.96, but it might be 2.5. So if you have just a few amount of observations, you need to find a difference that is larger than 2.5 standard deviations or standard errors of mean to the right or to the left, which basically just implies that the lower number of participants you have, the larger your difference needs to be to actually conclude that there is a difference. Other than that, you will see that this formula looks almost exactly the same. It's the mean you observed minus some expected value divided by the standard error of mean. Well, what do I mean with this expected value? I'll come back to that in a minute when we go through some examples. Because this t-test, or this formula that I showed you, you can use this in different ways. But actually those ways are not that different at all. They're all based on the same formula. That's why it's a T formula or T test. But you can use it in different situations. For example, and up until now I talked very theoretical, and it may be a little bit of mumbo jumbo up until now, and maybe you're not following everything. But now I'm going to give some clear examples, and I hope with that it also becomes clear what I mean with critical value and what I mean with being significant and all that kind of stuff. So we will come back to that now. So there is something called a one sample t-test, and that is when you have a certain sample of observations. So you run an experiment and you test this to an expected value. Now, in psychology and neuroscience, we often do not have an expected value, but sometimes we have. For example, you could, for example, want to see if the average IQ score of a sample of students. I work at the University of Minnesota, so that's why it says UOM, University of Minnesota students, but just take random students, doesn't really matter. You could look if the average IQ score of students is larger than 100. So in that case, you have an expected value. Your starting point is this 100, right? And you want to see if average IQ, which is you get from a sample of students. Let's say you test 25 students. You test the IQ score of 25 students, and then you want to see if this average is larger than 100. That's one thing you could do. But typically, and I already gave some examples before, we compare different groups with each other rather than having it fixed around a certain score, right? In this first example, you have one sample, one experimental group, and then you compare this to a number that we kind of picked out of a hat. But typically you compare two groups with each other. Now then you can use, for example, a dependent samples t-test or a paired t-test or a paired samples t-test. In this case, you compare two averages with each other, but those averages come from the same participants. So for example, you could look at whether a certain score is different from 1 point, and then 1 week later you test them again to see if the score changed. Now, this dependent sample t-test, when you're doing two groups, or not two groups, two conditions, may seem quite different, but it's actually exactly the same. But rather than looking at the single observation, you just take the difference between the two observations. So you take the score of a certain participant at day 1, and you take the score of a participant of day 2. You subtract those two numbers from each other, which gives you one single number, a different score. And then you take this different score, and then you can put this in your t-test formula. And then, of course, under the null hypothesis, remember, the null hypothesis says we don't expect any difference. Your expected value, right, which in the first example was 100, is now 0 because we don't expect any difference from point 1 to point 2. So your expected value is 0. So when could you use these kind of dependent samples t-tests? Well, as I already said, you could look, for example, the difference from today to a certain score in next week. But you could also, for example, look before and after an intervention. So before somebody got some medication, after somebody got some medication. But you could also compare to conditions in a task. For example, people, what's the reaction time of people looking at a picture of a fish and determining whether that is an animal, or a picture of a bird, right? Could be that people are faster when looking at a picture of a bird, and then you would want to compare those two groups. And in this case, the same participants look at birds and fish, so you can compare this with a dependent sample t-test, because again, the dependent sample t-test is two scores from the same participants. Now, sometimes you don't have, you will have different means, but you're not coming from the same participants. You have two groups. For example, if you want to compare smokers with non-smokers, you cannot use the same participants, because you cannot have at time point one a person smoking and then or not smoking, and then ask them to start smoking to then look at the second score. You can't do that. That's ethically not okay. So sometimes you have groups that you cannot compare the same person. Here on the slide I gave the example of, for example, coffee drinkers versus tea drinkers. Some people drink coffee and some people drink tea, and you would want to compare them on IQ score, but those would be different participants, right? Now in that case, you would use an independent samples t-test of two independent samples. One group of participants, another group of participants. So typically when I refer to a independent samples t-test, I will refer to groups, whereas with a dependent samples t-test, I will refer to conditions. So let's actually take some examples and actually go through the statistics and calculate what the t-score would be and to see what that means. So again, here's our t formula, and let's start with this first example. We would want to see if the average IQ score of a group of students is larger than 100. Now let's say I collect the data from 25 students, and those 25 students had IQ scores ranging from 100, 101, 105 to 120 plus, and so on. I take the average of that, and then I find that on average those 25 students have an average IQ score of 112.3. Now I want to compare this to my expected value of 100, because I want to know if they're above average smart. So I take my observation, subtract that from the or I subtract the expected value, and then I divide by the standard error of mean. In this case, the standard error of mean is the standard deviation divided by the number of observations. Well, the number of observations is easy, it's 25, as I already said. The standard deviation, as I said, you can calculate this. For now, just trust me, I just picked a number, a realistic number of 15. As I said, this is just a realistic example, but in a real sample you would be able to calculate this. Now, and then you plug this in your formula, and then you can actually get a value, because 112.3 minus 100 is 12.3, divided by 15 divided by the square root of 25, and that is 5. It's 5. So it's 112.3 divided by 5, and then you get a t-score of 2.46. Now when you look at the results section of a paper, you will sometimes see between brackets a number behind your t, in this case 24, and that's what we call the degrees of freedom. And the degrees of freedom, that represents again how this t distribution looks like. As I said, this t distribution looks very much like a z distribution, like a normal distribution, except that it can be broader depending on the number of participants, and that is what is represented by the degrees of freedom. And the degrees of freedom is the number of participants minus 1. So in this case 25 minus 1 is 24. Now our t-score is 2.46, and our critical value for a t-score or a t-distribution with a degrees of freedom of 24 is 2.06. Again, remember, with the z-score, the critical value was always 1.96. But as I said, with the t-distribution, it depends a little bit on how many participants you have. So the more participants you have, the closer it gets to the z-distribution. The less participants you have, the broader it is. In this case, we don't have an infinite amount of participants. We have only 25. So our t-distribution is a little bit broader, which means the critical value is 2.06. And what does that mean? Remember, that critical value tells you when there is only 5% or represents the 5% most extreme values. So there's 2.5% to the right and 2.5% to the left. So in this case, if your t-score is larger than 2.06, or if your t-score is smaller than minus 2.06, then you have an observation that is in that range of the highest or lowest 5%, or the highest 2.5% and the lowest 2.5%, right? Because those 2.5 and 2.5 sum up to 5. And in this case, that is the case, right? Because 2.46 is larger than 2.06, so that is in that extreme part of the distribution. And that's why we say that the p-value, and that's the probability value, remember those are probabilities in this normal distribution, is smaller than 0.05. Actually, with the exact p-values you can calculate as well, but without that you would even know that it is smaller than 0.05. So what does that mean? So that means that the chance of students having an average IQ score of 100, or right, so which would mean that the students having an average IQ, that is very unlikely, because the chances of that being the case is smaller than 5%. So the chances of students of the University of Minnesota having an average IQ that is around 100 has a chance of smaller than 5%. So what we would conclude here is that the null hypothesis is false, right, that they are around 100, and we would accept the alternative hypothesis, in this case that the average IQ score is larger than 100, which means that we can conclude from this that it is highly probable that University of Minnesota students have an above average IQ. And that's how you get to that conclusion. Do we know 100% certain that students have an above average IQ? No. But that's what I already said before. In statistics, you can never be 100% certain. You can only say it's very unlikely that that the null hypothesis is true. Where it is that they have an average IQ. And since that is very unlikely, it's way more likely that they have an above average IQ. Coming back to the court example, you could say it is very, very unlikely that the defendant is innocent. And because it's very unlikely that he's innocent, he must be guilty, or he's very likely to be guilty. And that's how you come to that conclusion. Now, you could, for example, say, well, but there's still a chance of around, let's say, 5%, or maybe it's 4 or 3%, that this could be just on chance, right? Because that's what your p-value says. The fact that we observe this score of 112.3, there is a chance of smaller than 5% that this would be the case if they would have an average IQ score. Now you could say, okay, 3, 4, 5%. There's still a chance though, right? And if you as a researcher think that this chance is too high, you could, for example, say that, okay, I only accept something to be a significant difference if the p-value is smaller than 0.01. And in this case, or in that case, your bar of when you call something significant is higher, right? Now, in psychology and neuroscience, we typically go with the 0.05 value. Over more than 100 of years, we found out that that is probably the most realistic one. Now, you could be more strict by lowering this value, but that has some other problems as well. But I will come back to that in a minute. Now let's look at the example of a dependent samples t-test. So where we have two conditions where we have the same participants, but at different time points or at different conditions. Now, for example, you could look at if IQ score changes from before or after an intervention. Now in this case I used the intervention of TDCS. TDCS is transcranial direct current stimulation, which is a technique that I use myself quite a lot, but you could use any intervention. You could also say some kind of drug intervention. Doesn't really matter for this example. Let's just say if IQ scored before an intervention, or if it changed after an intervention compared to before an intervention. So in that case, of course, you have the same participants before the intervention and after the intervention. So same participants means dependent samples. Now, when you look at the formula and compare this to the last slide, you will see that it is almost similar, except that there is a small d now at the x bar, which is our mean, and the standard deviation. And that is just to imply that we're not talking about a difference. So, for example, you could have participant number 1 who had before the intervention an IQ score of 101, and then after the intervention he had an IQ score of 103, which means his difference score would be 2. And then another participant could have a score before of 100 and then afterwards of 98, and that participant would have a difference score of -2. So if you have 25 participants, you can calculate all these difference scores from after minus before. You do that for all of them, and then you just take the average again, the average of those difference scores. And that's then basically what you plug in into your formula. So in this example, I just again made up some numbers, and let's say that the difference score, the average difference score is 3.1. Which means that on average participants scored 3.1 IQ points higher after the intervention than before. Now, and then you see in this formula again is minus mu0, which is your expected value or your null hypothesis value. And of course we don't, under the null hypothesis, we don't expect there to be a difference from pre to post, because our starting point is always that there is no difference. So our expected value is 0. That's why in some statistics book you will also see the dependent samples t-test. If you look at the formula, that this minus mu0 is just gone, it's just cut out, because the expected value in a dependent samples t-test is always 0. So that's why you can basically leave that out. And then you divide it again by your standard error of mean. Again, the standard error of mean in this case is about the difference scores, so that's why this value is a little bit different. I again used a realistic number of 6, but as I said, this is just a number, and then we divide it by the number of participants, the square root of that, and then you can calculate it again. In this case we would have a t-score of 1.55. Our critical value is the same as the last because we still have 25 participants, which gives us a degrees of freedom of 24, which means our distribution of our t-test is exactly the same as before. So our critical value is 2.06. And then we would see that 1.55, again, which just means that the post-test score is 1.55 standard deviations larger than the pre-test score. So that is smaller than this critical value, after which, again, if it's larger than the critical value or smaller than the negative of the critical value, then we would say that the chance of that happening is very, very small. In this case, the chance is not so small. The chance of this happening is larger than 5%. So in our distribution, remember, it falls more into the middle. So a score like this could actually be just on chance level, or the chances of that being the case is larger than 5%. And if a chance of this happening is larger than 5%, we cannot make the conclusion that there is a difference from pre to post. This doesn't necessarily mean that this intervention didn't have an effect. It just means that this intervention, or the effect of this intervention, was too small for us to make a conclusion about. Because now we have to accept the null hypothesis that the difference from pre-test to post-test wasn't different. But that doesn't necessarily mean that there is no difference at all. Because again, remember, you cannot conclusively show that you cannot conclusively prove a negative. The only thing we can conclude from that is that there is not enough evidence to show that there is a difference. All right, but other than that, you will see that this dependent sample t-test is actually really the same as a one sample t-test. All right, so let's go to the next example, which is the independent samples t-test. Now, with the independent samples t-test, we're comparing two groups with each other of different participants. So that could, for example, be coffee drinkers versus tea drinkers on an IQ score. Now, when you look at the formula for this t-score, it may look a little bit different than the last one, right? It looks a little bit more complex, but actually it's not that much different, because rather than having just one mean score that we compare to the standard error of mean, we here have two mean scores that we have to subtract from each other. So why do we have to do this? Because in the paired samples t-test, we could look at the different score from before and after an intervention. Now here we can't do that because we have two different groups, so there's no pairing of values, right? So the only thing you can do is subtract the mean scores from each other, and that's what happens here in the top part of this t formula, where you subtract the two mean values of the two groups that we're having, in this case coffee drinkers and tea drinkers. And also below you will see that this looks a little bit more complex than your standard error before. The standard error was just the standard deviation divided by the square root of the number of observations. Here it looks a little bit more complex, but actually it's not that much more complex, because you again see the S, which stands for standard deviation, and then you see 1 divided by n2 plus 1 divided by n1 and 1 divided by n2. And these are just the number of observations for each group, so the number of coffee drinkers and the number of tea drinkers. And the standard deviation is still the same standard deviation, except that we now take a mean of the two standard deviations, because each group has a standard deviation, and we take kind of the average of that. It's called a pooled standard deviation. It's not exactly an average, but it's more or less an average. And when you look at this formula, you can also, you could put this s squared also instead of the 1 here, instead of the 1 here, which means then you would get the square root of s squared divided by n1 and s squared divided by n2. And that is, of course, very similar to what we had before, except that we have it now twice for each group. So when we look at an example, and I again just took some numbers, let's say that the average IQ of coffee drinkers is 104.2 and the average IQ of tea drinkers is 107.8. And then we divide this by the pooled standard deviation, or the square root of the pooled standard deviation squared. And here I just made up a number, which is 10.22, multiplied by 1 divided by the number of participants in the coffee drinkers group and 1 divided by the number of tea drinkers. In this case, I choose that there are 60 for each group, which means that we have a total sample of 120 people. Now, when we then calculate the t-value, you can calculate this, and then you will see that it is 1.04. Now, there's a little change from the last time, because you now see that between brackets there is not 24 anymore, but now it says 118. Now, before I said the degrees of freedom is the number of observations minus 1. Now, in this case, you would think, okay, but there are 120 observations minus 1, that's 119, right? And not 118. Well, for the independent sample t-test, it's the number of observations minus the number of groups. And actually that's always the case, because in the one sample t-test we only have one group, and in the paired sample t-test we have one group of different scores. Now in this case we have two groups, so it's the number of observations, which is 60 plus 60, which is 120, minus the number of groups, which is 2, so 118. And that does change something, because that changes that critical value. in our example before, we saw that the critical value was 2.06, which meant that everything larger than 2.06 is in that zone where it's very unlikely to be based on chance, or if it's lower than minus 2.06. Now, as I also said before, is with more observations, this t-distribution becomes a little bit more narrow. And as you can see here, indeed, the critical value therefore moves a little bit more inwards, which means that our critical value is now 1.998, which is very close to that 1.96 we saw before for the z-distribution, which, remember, is the same as a t-test, but then for an infinite amount of participants. So, yeah. So now we're going to look at if our t-value is larger than 1.98, or if it's smaller than minus 1.98. In this case, this is not the case because 1.04 is smaller than 1.98. Which means that the observation we have here, the observation that we would see a IQ score and mean IQ score of 107.8 in a coffee drinkers group rather than in a tea drinkers group, or an IQ score of 104.2 in the tea drinkers group rather than in the coffee drinkers group, that chance is relatively high, or it's at least higher than 5%, which means that we from this conclude that there is no significant difference between the groups. Tea drinkers, although their mean is a little bit higher than that of coffee drinkers, that difference is probably just on chance level. And the chances of that happening is larger than 5%, so that's why we say there's no significant difference between those two groups, because this could just happen on chance. Again, just as with the dependent t-test, we are not 100% certain now that there is no difference between coffee drinkers and tea drinkers. We just don't have the evidence to show that there is. All right. So now we went through all the examples of all the t-tests. As I said before, like in one lecture, you cannot understand completely statistics. So what I would suggest is that you take some other examples and just go through those formulas and calculate what the actual t-value is and compare it to the critical t-value. And you can always look up the critical t-value in either a statistics book or online. And then just, go through 3, 4, 5 of those examples for yourself and try to see, can I find whether two groups are significantly different from each other or not? Or is a certain value different from an expected value? All right. So, yeah, but you can, of course, do all these examples at home. But I will now move on, because right now we always talked about when we have either one group or two conditions. But what happens if we have more than two groups? What happens if we have 3 conditions or 3 groups? For example, coffee drinkers, tea drinkers, and water drinkers, and if we want to compare those on an IQ score. Now, in that case, we need to do something different, because if you look at this formula, we can subtract x1 minus x2. But we couldn't subtract 3 values from each other, because that wouldn't make sense, right? So if we want to compare 3 groups with each other, we have to do something different. And this is what is called the analysis of variance, or it's also called an ANOVA. And ANOVA is something you will see in a lot of research papers, psychology research papers, and also in neuroscience research papers. So that one is something that you will see quite a lot. Now, just because you see the word ANOVA, or analysis of variance, that still doesn't tell you everything, because there are, just as with the t-test, different varieties of this ANOVA. For example, there is the one sample ANOVA, and that is an ANOVA of independent samples. So again, the independent samples means independent groups, which means that we have different groups, right? So we have tea drinkers, coffee drinkers, and water drinkers. Those are different people. If you want to compare those with each other, then you have you need a one sample ANOVA. Now then there's also something called a factorial ANOVA. And that is kind of the same thing. It's again based on different groups, But in this case, you're not only having one set of groups, but you're having two or more set of groups. So for example, if you would want to compare coffee drinkers, tea drinkers, and water drinkers on IQ score, but you also want to distinguish between whether they're young or old. So you have young tea drinkers, young coffee drinkers, young water drinkers, and old tea drinkers, old coffee drinkers, and old water drinkers. Is that the one I had left? I don't know. But so if you want to make that distinction of two sets of groups, so young versus old and coffee versus tea versus water, then you need a factorial ANOVA. And then there's also something called a MANOVA, which stands for multiple ANOVA, or multiple factor ANOVA. And this is a ANOVA if you have multiple dependent variables. Remember, the dependent variable is the thing you measure. So if you would, for example, want to see if tea drinkers, coffee drinkers, and water drinkers differ not only on IQ score, but also on some kind of test score, some kind of exam score, you want to look at whether those groups differ on one score and on another score, then you need a MANOVA, because that looks at those two scores at the same time. For example, you could also look if some people before or after, or some people who got a medication or some people who didn't get a medication, if they differ on both reaction time and accuracy, which are also two measures, and then you could look at them at the same time. Now, those three examples are all when you have independent samples, so different groups, right? But as I said before, it could also be the case that we just look at different conditions, right? We have the same participants that we just test multiple times, for example, before and after an intervention. Now, if you have three conditions, for example, before an intervention, during an intervention, and after an intervention, we cannot use a t-test anymore, but we have to use an ANOVA. In this case, it's called a repeated measures ANOVA. I guess that name makes quite sense. It's sometimes also referred to as a repeated measures MANOVA, and the reason for that is that if you would look at how this repeated measures ANOVA is structured, it is not that much different from a independent samples MANOVA. Now that seems really weird. How can a dependent samples test of different conditions be the same thing as a test for independent samples? Well, it's because in a ANOVA with repeated measures, each of those time points or each of those conditions is treated as a different dependent variable. And that is why it's sometimes referred to as a repeated measures ANOVA. Now, that is really not that important. So if that seems a little bit fake, just ignore that. All right. And then, of course, you could have the case where you want to compare different groups, but also different time points. For example, before, during, and after an intervention, you want to compare coffee drinkers, tea drinkers, and water drinkers. Well, in that case, you mix everything together, and as the name already says, then you will get a mixed model ANOVA. Now, I won't go through all examples of this because that would take forever, but just note that although they are different, the basic principles are the same for all of them. So let's have at least a look at how we would calculate some parts of this ANOVA. As I said before, you cannot really subtract three groups from each other, so you have to calculate something in a different way. And that's what we can calculate is the sum of squares. And the sum of squares is not one thing, it's actually two things. You can have the sum of square between groups and the sum of square within groups. And the sum of square between groups tells you a little bit about how the means of the different groups differ. Tea drinkers, coffee drinkers, water drinkers, how do those means differ from each other? And the sum of squares within groups tells you a little bit about how the different people in each group score. So for example, the first coffee drinker, how does he score from the third coffee drinker? How is that difference? So how would you calculate this? So the sum of square between groups, as you can see in this formula, is x bar, j, and j stands for a certain group, minus x bar, without the j, and that's just the overall average. So what does that mean? For example, if you have if your coffee drinkers, they score an IQ of 100, then the tea drinkers score an IQ of 110, and the water drinkers score an IQ of 120. Now, before you can plug it into the formula, you first have to calculate the overall average, so the average over those three groups altogether. Now, in this example, if all those groups have the same amount of participants, that would be 100 plus 110 plus 120 divided by 3, which is also 110. So to calculate the sum of squares between groups, what you would have to do is you now subtract each group's mean from that overall mean, and then you square it and then you sum it up. So that would be 100 minus 110 squared plus 110 minus 110 squared, which is 0, and then 120 minus 110 squared. So in that case you would get 100 plus 0 plus 100, which is, we would get a sum of squares between groups of 200. Now, the sum of squares within groups, as I said, tells you a little bit about the differences between the different individuals or the different scores within each condition. So in that case, we'll take an individual score and you subtract that from the mean of the group. So remember, in our example, the mean of the coffee drinkers group was 100. Now, the first coffee drinker maybe scores 98. So that would then be 98 minus 100 squared. Plus the next score, which may be 107. 107 minus 100 squared. Plus and so on. And you do this for all observations in each group, and you all sum it up for all the groups. And so why would we do this? Because the sum of squares between groups tells you how much the different group means vary from each other. So if you look at the group level, how much do those groups differ? Whereas the within group level, that tells you more about how individuals differ. Now, how much individuals differ, that is just random differences that we are not interested, right? Because the groups, that is what we manipulated. We created those groups, or at least we tested those groups, right? We specifically look for coffee drinkers, tea drinkers, and water drinkers because we expect something to be there, right? However, the difference between two people, Josh and Joe, that difference between two random people, that difference we're not really interested in. So that is just a difference that just happens in the world we're not interested in. Now, if we want to compare these two sum of squares with each other, we have to account for the number of observations, because of course the sum of square group, the sum of square of the different groups in our case has just three values, right? It's just the mean minus the overall mean for the coffee drinkers and the tea drinkers and the water drinkers summed up. Whereas within groups there are a lot more observations, right? There are a lot more people than groups, obviously, per definition. So the sum of square for the within groups is typically larger than that between groups. So we have to account for the differences in the amount of calculations we make, basically. And that's what we call the mean square between groups and the mean square within groups. Now, the mean square between groups is just the sum of square between groups divided, and you would think by the number of groups, but again, we use this degrees of freedom, which is the number of groups minus 1. So in this case, the small letter k stands for number of groups. So the degrees of freedom in our case with the coffee drinkers, tea drinkers, and water drinkers would be 3 minus 1, which is 2. So our sum of squares between groups, which was 200, we divide that by 2, which gets 100. And then the mean square within groups, is the same thing. It's just the sum of square within groups divided. Again, you would think by the number of participants, but it's the number of participants minus the number of groups. right? So in our case, that would be, we didn't define the number of participants, but let's say there's 60 in each group, which means 60 plus 6 plus 6 is 180, minus number of groups, which is 3, so the degrees of freedom for the within groups would be 177. So then you get kind of like an average variability between the groups and an average variability within the group. So how much do the group means differ from each other, and how much do people in general differ from each other without taking into account any group. And then you can subtract it by each other. Not subtract, you can take a ratio of that. And what that gives you is how much more or how much less are the between group differences compared to the within group differences. Because as I said before, the within group differences, those are just differences between different people that we would expect, because people just differ, right? Harry and Pete, they score differently. That's just the case. But how much more do people differ if they are coffee drinkers versus water drinkers versus tea drinkers compared to just some random differences? And that's what you calculate with this so-called F-score. And the F-score is basically just the outcome value of an ANOVA. So this gives you a ratio. For example, if the F value would be 3, then there's 3 times more variation between groups than within groups, which means that the fact that a coffee drinker scores higher than a tea drinker or a water drinker, that difference is 3 times larger than just the difference between 2 random people. Now, when you calculate this ANOVA, you will know that at least one of those groups, and it is significant, so we get a p-value of smaller than 0.05. And again, for the F score, you also have critical values that you can just look up, right? But if an ANOVA is significant, that implies that at least one group is different. But it could be that 2 groups are different, or that all groups are different from each other. You don't know yet which groups differ from each other. It could be that water drinkers are better than coffee and tea drinkers. It could be that tea drinkers are better than coffee drinkers, who themselves are better than water drinkers. We don't know that yet. So to figure that out, we again have to go back to our t-tests. And then we do 3 separate t-tests. In this case, would be, of course, 3 separate independent sample t-tests. I'm saying 3, but actually you would do more, right? You would compare group 1 versus 2, 2 versus 3, and 1 versus 3. Well, that's 3 tests. But of course, if you have 4 groups, that would be more than 3 tests. Now, one thing that you have to be careful is that, as I said before, when do we determine that something is significant? We determine that something is significant if the chances of this being the case just randomly are smaller than 5%, right? That's what this p-value of smaller than 0.05 meant. The chances that we would just randomly observe this observation, this chance is smaller than 5%. However, if you repeat a t-test 3 times, then it's the first time 5%, the second time 5%, and the third time 5%, which means the chances of you observing something purely on chance, although there's no real difference, is 15%, 3 times 5. And that, of course, would be a little bit unfair, because when we, in other tests, say, okay, we only say that there is a significant difference between groups if the chances of this being random is smaller than 5%, then if we now take 15%, that's just unfair. So what we typically do is, when we do those so-called post hoc t-tests, is that we use a correction for this significance value. And there are different ways to do it. One is, for example, the Bonferroni method. And the Bonferroni method is to basically just divide your significance level by 3. Or by the number of tests you do. In our case, with the coffee drinkers, tea drinkers, and water drinkers, that would be 3. Of course, if you make more groups or more comparisons, that would be a larger number. So what we then would say is that something is not significant at 0.05, but something is significant at 0.05 divided by 3, which is 0.0167. So only if our p-value is smaller than 0.0167, then it's significant. You could also do the other way around. You could just divide your p-value by 3, right? So now you would say, okay, of course, it's always nice to be as strict as possible, right? But imagine doing this for not 3 groups or 4 groups, but for 100 groups or 1,000 groups. And you would think, well, who is going to do 1,000 comparisons? Well, actually, if you do fMRI studies where you look at different voxels are the little pixels within an MRI scan, that can go up to 1 million. Or if you have EEG channels and you want to compare the different EEG channels with each other, you sometimes have 128 channels, and all those different comparisons are an even much larger number. So it could be that you would have to do a lot of t-tests. Now in that case, if you would use this method of just subtracting your significance level by the number of tests you did, then you would have to find very, very small p-values to still find a significant difference, right? Because as we said, with this Bonferroni method, we divide the significance level by the number of tests we do. So if you do 1,000 tests, then you wouldn't say something is significant at 0.05, but something would be significant if it's smaller than 0.000005. And that can be problematic, not only because that is just very rare, but also because you get a problem with a so-called type 2 error. Now, what's a type 2 error? First of all, before we talk about type 2 error, we of course have to talk about the type 1 error. The type 1 error is basically just a technical term for the chances of you being wrong when you say that something is significant. So for example, if we say something is significant at 0.05, again, what does that mean? That means that the chances that we would observe this just pure on chance is 5%. And that's like a different term for that is a type 1 error. So the type 1 error is the chance of you observing something on chance while there is no actual difference. So type 1 error is basically just another word for your significance level that you choose. And if you choose 0.05, then your type 1 error is 0.05. So the type 1 error tells you something about you call something significant. What is the chance that that might be wrong? And of course, you would want that error to be as small as possible, as we talked before. However, there's also the type 2 error, and that is the exact opposite. You call something not significant while there actually is a significant difference. Basically, you didn't find the difference, although there may be. There is no difference between coffee drinkers and tea drinkers, although there actually is. That's called a type 2 error. And when you compare those type 1 and type 2 errors, those are related with each other, right? Because if you are very strict on your type 1 error, you say, I'm only going to call something significant if it's smaller than 0.000001%. Then, of course, the chance that you didn't find something significant that actually is starts to increase as well, right? So there's always a balance between type 1 and type 2 error. So that's why we often go with a type 1 error or a significance level of 0.05. That may seem still like too big, right? It may be the case that you think, okay, the chance that I observe something randomly is 5%, so why would I call that a significant difference? Well, if you go much, much smaller, then yes, you will only find significant differences that are actually significant, but you may miss a few significant differences that are also significant, but you just didn't find. Now, what can you do to make your type 1 error as small as possible, as well as your type 2 error as small as possible? Just test more participants. The more participants you test, the smaller your standard errors become, because remember, the standard error is the standard deviation divided by the number of participants, right? So if you have more participants, your standard error of mean becomes smaller as well. And if your standard error of mean becomes smaller as well, remember, that means that your distribution becomes narrower. Now, in this example here on the screen, you see two distributions, and if you would make them narrower, both of them, then you would automatically see that both the greenish and the red area would become smaller as well. So that's what you can actually do to make a type 1 error and type 2 error different. But if you have a certain number of participants and you can't make that bigger for some reason, or you stop testing already or whatever, then it's always a balance. So if you make those hundreds or thousands of comparisons and you make your type 1 error smaller and smaller and smaller and smaller, then the chances of you finding not a significant difference that's actually there start to increase as well. So it's always a balance. So that's why this Bonferroni method of correcting is not always the best. And there are different methods to do that. You could, for example, do something called permutation testing, which kind of avoids this problem altogether. Now, what that is, I won't be talking about today. That is a topic for a different lecture, but yeah, just know that there are different options. Now, when you do an ANOVA, I said you can also do this with multiple dimensions, right? So, for example, you could compare the coffee drinkers, tea drinkers, and water drinkers, but you can also look at the difference between young and old, right? And then you would get a graph which resembles the thing on the left here on the screen, where you have three values, tea drinkers, coffee drinkers, and water drinkers, in one side, but also for the other side, young and old. And what we can observe here is a so-called interaction effect. So not just the difference between young and old, but or a difference between coffee drinkers and tea drinkers and water drinkers, but those effects could interact with each other. It could, for example, be that young coffee drinkers score higher than old coffee drinkers, but for the tea drinkers, it's the complete opposite. Old tea drinkers score higher than young tea drinkers. So that means that there is an interaction between those two effects. There is an effect of young versus old, but it really depends on whether you are a coffee drinker or a tea drinker. And when you have something like this, you can also follow this up with multiple t-tests to find out how this interaction exactly looks like. And these are so-called simple effects. Now let's talk a little bit more about those interaction effects. And I go back to the example of just having two groups because that makes it a little bit easier to interpret. Let's just say coffee drinkers and tea drinkers, and young versus old. Now, you will find interaction effects a lot in papers, and you will see that also in different graphs. And I think it's good to just look at some graphs to understand how an interaction effect or a main effect could look like. Now let's take the first example here, where you have this basically this those crossed lines. And let's say that the blue line are the coffee drinkers and the orange line is the tea drinkers. And A, the left part is young, and B, the right part is old. So for the coffee drinkers, which was the blue line, it means that young people, they score very low, right? On the left side, the blue line is very low. But on the right side, the blue line goes up, or it's very high, which means that young coffee drinkers score low, old coffee drinkers score high. But for the tea drinkers, it's the opposite. the young tea drinkers, they score very high, whereas the old tea drinkers score very low. And this is a typical interaction effect, where there is a difference between young and old, but it depends on whether you're a coffee drinker or a tea drinker. Now, in this case, there are no main effects, because if you would look at young versus old overall, you wouldn't see a difference. For example, if you just look on the left side, if you take the average of tea drinkers and coffee drinkers, then you would get somewhere in the middle, which means that on average, young people have a certain score in the middle. But then if you look on the right, if you average that as well, old people, on average, regardless of whether they're tea or coffee drinkers, have a certain score in the middle as well, which means that young versus old, overall, not taking into account coffee or tea drinkers, there's no difference. And the same is true for coffee drinkers, for tea drinkers overall. If you don't look at age, then you would be in the middle of A and B, basically. You see that there is no difference between the coffee drinkers and tea drinkers if you disregard age, or if you would just take an average age. And that just shows that sometimes it's really important to have those multiple factors in your ANOVA, because if you would just be looking at coffee versus tea drinkers, you wouldn't find the difference. But then if you also take into account another factor, you would see that there actually is a difference. And that is why it's sometimes important to have multiple factors in your ANOVA. Now, you could also have an interaction effect, but still there would be a main effect. So for example, in the second graph, you see that the blue line, which were the coffee drinkers, this line is very low for young people and gets a little bit higher for older people. So basically, young coffee drinkers score very low, and older coffee drinkers, they score a little bit higher. For the tea drinkers, it's the opposite. The young tea drinkers, they score very high, whereas the older tea drinkers, they score a little bit lower, but still averagely high. So there's still an interaction effect, right? Because it really depends on whether you're a coffee drinker or a tea drinker, and whether you're young or old. If you're young and tea drinker, you score very high, and that just becomes worse. But if you're a coffee drinker and you score very low when you're young, it only gets better. So there is definitely an interaction effect. But there is also a main effect, because you see that the orange line is always higher than the blue line, which means that tea drinkers are always better than coffee drinkers. But there is no main effect of young versus old, because if you take the average of young people, so the average of the left part of the graph, then you would see that meets somewhere up in the middle, and in the right part for the old people, if you average that, that also meets up somewhere in the middle. So there's no effect of young versus old, because, as we said before, the effect of young versus old really depends on whether you're a coffee drinker or a tea drinker. But on average, if you disregard coffee versus tea, then there's no difference between young and old. Again, it just shows why it's so important to have multiple factors in your ANOVA. And then there finally is an example of where there is an interaction effect with two main effects. Now, again, there is a main effect of tea versus coffee, because the orange line is on average higher than the blue line. Now you will also see that on average, young people score lower than old people, because for the old people the lines are both higher than for the young people. But there also is an interaction effect, because for the coffee drinkers there is a massive increase in score when you become older. But for the tea drinkers, there's still an increase, but it's a lot smaller. So this is how, when you see those kind of graphs in the paper, would have to interpret that. And then if you go in the results section and you find something that really doesn't fit with your expectation, then your bullshit detector should go off. Now, in the beginning of this lecture, I said that your independent variable, so the thing you manipulate, can be either categorical or continuous, right? It could be different groups or different conditions, or it could be just a range of values. Now, up until now, everything we did now, we only had independent variables that were categorical. We always looked at different groups, coffee drinkers, tea drinkers, or different conditions, before an intervention, after an intervention, you name it. Those are separate conditions. Those are things that do not fall on a continuous line. However, we could look at a continuous variable as well. For example, we would want to know if BMI has an effect on IQ, and BMI is just a range of scores, right? You could divide people into a low BMI group and high BMI group, right? But then you create those groups. But if you don't create those groups, your BMI is just a score from whatever, 18 to, well, could be very high, but doesn't really matter. Now, you can have those type of continuous variables in an ANOVA, and then we would call it an ANCOVA. And the C stands for covariate, because a covariate is a continuous variable. So then you could, for example, do an ANOVA on tea versus drinkers versus coffee drinkers versus water drinkers on IQ score, but you take this BMI score in there as well. However, basically, on the basis in an ANOVA or an ANCOVA, you always have at least one categorical variable, independent variable. So if you would just want to look at BMI score on IQ, then the ANOVA is not the right thing. In that case, you would have to do a linear regression. And a linear regression, you could do a regression in general. A regression just means that you regress, which means you draw a line between two variables, and you can only draw a line between two variables if they're both continuous, right? As we said before, our dependent variable, the thing we measure, reaction time, IQ score, you name it, those in our examples were always continuous. But if your independent variable is also continuous, for example, BMI score or height or income, then you can basically draw a line between that, and that's what a regression analysis is. And if this line is linear, then we call it the linear regression analysis. That line doesn't need to be linear, but that again would be some more advanced statistics that I will be talking about in another lecture. Now, just as a quick intermezzo here, you can write down an ANOVA as a linear regression. Now, that may seem weird because we talked about this f-test and the sum of squares and the mean of squares, and then you get this f value, and this doesn't seem to have to do anything with a linear regression. But actually, you can rewrite this as a linear regression. What you would have to do is, though, you would have to give numbers to your different conditions. For example, you would have to call the coffee drinkers group 1, tea drinkers group 2, and water drinkers group 3. Now, of course, those numbers wouldn't then really have the meaning that the numbers typically would have, right? Usually, like 2 means 2 is 2 times larger than 1, and 3 is 3 times larger than 1, and 1.5 times larger than 2. Now, that is, of course, not the case, because those numbers then wouldn't have meaning, but you still can rewrite it as a linear regression. Now, if you look at this formula, which looks quite complex, this formula up there is just a line between the two variables. So you have an x-axis and a y-axis, and then you can draw a line in there. And this line within this let's take this example here. So you have here you have the formula here as well. Again, you have an x-axis which goes from 0 to 120, and then you have a y-axis which goes from 0 to 180. Now, there are different dots, which are different observations, different BMI scores. Well, okay, probably not BMI scores because they wouldn't go up to 120, but it doesn't really matter. What could this be? Weight. Well, no, weight is also a bad example. Well, just take some random x variable And then on the y-axis we could have IQ score. That seems more or less realistic. It doesn't really matter. But you have those different observations, and then you can draw a line between this. And this second formula here on this slide as well, it's the same formula as on the previous slide. That is basically just how this line looks like. So you have here this beta 0, which is the Greek letter for B, and that is just the weight of something. So you have this beta 0, and this beta 0 reflects this, the intercept. And the intercept is where the line crosses the y-axis. So in this case, this would be around somewhere 50, 55-ish. So this B0 in this example would be 55-ish. Plus, and then in this case, there are only two variables, the one independent variable and one dependent variable, which means that in this example, there would only be 0 and B1. Those B2 and everything else you can ignore, because that wouldn't be the case here. Now you could do this with multiple variables, and then you would have to calculate this down, and then it would be a little bit harder to represent this in one graph, but I will come back to that in a few minutes. So in that case, the beta 1 here refers to the slope. So for example, if I go 10 points, or if I go 1 point up on the x-axis, how much does my y-axis go up? Now, for example, here you could see that if you go 20 to the right, then it goes up by a little bit more than 20, right? So so that means that if you go 1 up, it goes a little bit more than 1 up. And that's actually the case, because actually I have the formula here, which is the same as this formula on the left, except that there's no bx2 and something like that. And so the slope is 1.08, which just means if I go one step, if I go from 20 to 21, I, on the y-axis, go from 70 to 71.08. And here, plus the intercept, now in this case the beta 0, that's the intercept. Now I just put it at the end rather than the beginning. And I estimated it to be between 50 and 55. It's a little bit lower, it's 46. But okay, if we draw this line through 0, then I mean, it could be 46. So yeah, that is the case. Now, when you took this formula, I said the B2 and B everything else you can ignore if there's only one variable. There's also this E, which is just the error, which is just everything that is not explained by this line. And I mean, obviously those dots are not fully explained by the line, right? Because not all dots are perfectly on this line. If that were to be the case, then it would just be, this would be this E, or this epsilon, or this Greek letter E, would be, which stands for error, would be 0. Now this is not the case here. Now you can also represent how well this line fits those dots by something called a correlation. And a correlation and a linear regression, they always go kind of hand in hand. If you have linear regression, you can easily calculate a correlation. And if you have a correlation between two variables, you should be able to calculate a linear regression from that. And a correlation basically just is one number that represents how well those dots fit that line. So if they would perfectly fit that line, then your correlation score would be very high. Whereas if those dots really are all over the place and the line is just somewhere randomly in the middle, then your correlation is very low. Now a correlation can vary between -1 and +1. If it's close to -1 or if it's close to +1, then the line very well represents those dots. So in that case, the dots would be very close to the line. Now, what's then the difference between +1 and -1? Well, +1 just means that there is a positive relationship. So if I go up with x, then also y goes up, as would be the case here. But if the correlation is -1, there would be a negative relationship. So if x goes up, then y goes down. But other than that, the closer the number is to +1 or -1, the better this relationship is. Now in this case, before I move on to that, you can also take the square of your correlation. So the correlation is abbreviated by R. It's like the technical term for this type of correlation is Pearson correlation. There are different types of correlation, for example, a Spearman correlation. This is technically a Pearson correlation. And if you take the square of that, then that is something we call the explained variance. And the explained variance, remember, it's just the square of R, now becomes a number between 0 and 1, right? Because, of course, the negative values would then become positive if you square them. And that, again, tells you a little bit about how well those lines, how well those dots fit the line, obviously, because it's just the square value of the original correlation. But we call it explained variance, or because it is basically a percentage of how much of those dots, to what extent you can this line explains what's going on. So in this case, in this example here, the R squared value is 0.4726. What that basically means is that the variable x, or this line, the variable x, explains to 47% the variable y. So for example, let's take some real life examples. BMI on IQ score. Again, this is kind of a stupid example because I don't think BMI does explain anything about IQ, but whatever, let's just take the example because I don't know any better examples right now. If that were to be the case, then we would say that, okay, if we know BMI, then we, for 47%, can explain what IQ is. Or with a 47% accuracy, we could say what IQ is. Which means that if BMI goes up or down, then IQ varies as well. It wouldn't be a perfect explanation, right? There could be still some other factors, and that's represented by this epsilon value here. There are some other explanations about IQ score. For example, income could also be a factor. Again, it's a stupid example, but it doesn't really matter. And that would then be part of that 53% that is not explained yet. So the 47% is explained, and then 53% is not explained, and that part that is not explained is explained by other factors. For example, income. Let's say income is another 10%. Then we would already be up to 57. And then you would have to find all factors that explain this relationship perfectly. Now, trust me, in psychology and also in neuroscience, you will almost never have a perfect correlation. You will never be able to explain everything because differences between people and differences on things like IQ score, they are so random and variable that you will never be able to explain everything. Now, I wanted to explain something with this slide as well, but I'm not sure because it looks quite the same. So let's move on. So as I said, you can also have multiple factors in a regression analysis, and then we would call the regression analysis a multiple regression. So we have our dependent variable in this thing here, which was IQ score. And you could have the first independent variable, which then would be BMI, and the second one would be income. And those explain a little bit about the differences in IQ score. Now, when you do a multiple regression analysis, then we look at what each factor uniquely explains. So, because there might be an overlap between income and by BMI score as well, right? It might be that income already explains BMI score, and then if you would just take everything of BMI and everything of IQ, there would be some part that would be double, which is this part in the middle here in this picture. And of course, that is not something you want in your statistical analysis, because then you would sum up to, or you would use that area twice, which means that your explained variance would go up above 100%, which is obviously not possible. Now, when you do a multiple regression analysis, you throw in multiple factors. And what we typically do is that we start with all of them, and then step by step, we take those ones out that are not significant. You could also do it the opposite way. You start with one that is very significant and add multiple, and then add multiple factors. But most studies that use a multiple regression analysis throw in, let's say, 5 factors. They see that 2 of them are not significant. Then they take out the one that is least significant. Then they redo the analysis with 4 factors. Then they still see that other factor is not significant. Take that one out as well, and then remain with 3 factors that all explain the dependent variable. Now, as I alluded to before, is that a regression doesn't need to be necessarily linear. For example, in this case, we see that all the dots follow a certain curved line. Now, when we do a linear regression analysis, we again see that this linear line explains 47% of those dots. But if you look at this, you would say, but if I would fit a curved line through that, then that percentage must be a lot higher, right? That must be even close to 1, right? Because if I would fit a curved line in there, then that line would almost perfectly fit those dots. And that's what we call a nonlinear regression. And nonlinear regressions can be done with different types of lines. You could have a logarithmic function, an exponential function, a sigmoid function, you name it. And you can do this if you have the specific hypothesis for that. So in this case, in this example here, this would not be a good example of a linear regression analysis, because in a linear regression analysis, you would have to presume that your regression is linear. Now, before I close this off, I want to mention a few more things. And that is one thing that I mentioned before is assumptions. And already in the beginning, when I talked about the normal distribution, I said that we always start from this normal distribution, right? We need a normal distribution to do our statistics, to do our t-test, to do our ANOVA, because our t-test and our ANOVA, they depend on this normal distribution. If you don't have, if your data doesn't look like a normal distribution, then you have a problem. Now there is a second one, and that is called equality of variances. And that just means that if you have different groups, then how much variance there is within a group, that should be more or less the same between the two groups. So if you have the group of coffee drinkers, their scores should, if their scores range from 10 to 15, but then you have the tea drinkers group where the scores differ from 0 to 100, then there's way more variation in the tea drinkers group than in the coffee drinkers group. And that would be a problem if we want to do statistics with that. So what we want is an equality of variances. And those don't need to be exactly the same. They need to be in the same ballpark, basically. But yeah, they should be similar. Now, as I said before, this normality distribution is less of a problem if you have a large number of participants. And the same is true for the equality of variances. If you have a large number of participants, that problem becomes less and less and less. Now, I mentioned the normality assumption in the beginning. And I said that this would apply to all statistical tests we talk about today. And the same is true for the equality of variances. But we talked about so many different tests. So let's go quickly. I just want to quickly reiterate how it applies to each test. So when you have a between subjects design, where we have different groups, coffee drinkers, tea drinkers, water drinkers, then each of those distributions of tea drinkers, coffee drinkers, and water drinkers has to be normal. So that would be the case for your independent sample t-test, or your one-way ANOVA, or your factorial ANOVA. However, if you have a within design, so where you have the same participants coming back for different tests before an intervention or after an intervention, which would be in your dependent samples t-test or your repeated measures ANOVA, then each of those distributions has to be normally distributed, but also the distribution of the difference scores. Because remember, for the dependent sample t-test, we calculated difference scores. And the distribution of those difference scores has to be normal as well, on top of the distributions of each of the two conditions separately. And the same is true for the equality of variances. So in a between subjects design, the variances between each group has to be comparable. In a within design, it has to be the same. The variances have to be the same for each group, but also for the difference scores. And that's something we call sphericity. The assumption of sphericity. So when you see the assumption of sphericity, that's just the equality of variances. Now, you would say then, okay, but how does this apply to this regression analysis? Because that's something completely different, right? Well, actually, it's not. Because we still have some assumptions there. If you do a linear regression, obviously you want it to be linear, right? But you also want this distribution to be normally distributed, and that that there is an equality of variances. And then you would say, how is this represented? Well, that's something which we call homoscedasticity. And there is a picture in the lower part of the screen here right now where I show this. So homoscedasticity means that how much the dots on average differ from each other, so how much they vary from each other, should be the same at every point in the graph, or at least more or less. So in the left example, there is the homoscedasticity is the case, which means that there is equality of variances, because the dots, the differences between the dots is overall the same. Whereas on the right side, you see that that is not the case, because in the left part of the graph, the dots are relatively close to each other, whereas they broaden out like a fan the more you go to the right. And then the variance at the right part of the graph is a lot higher than the variance in the left part of the graph. And that's what we call heteroscedasticity. And that's a problem when you want to do a regression analysis. You should correct for that. Now, I said before, if you have a large number of participants, then all those both assumptions are not a huge problem. However, if your distributions are really, really skewed, then even with a large number of participants, it's not ideal. And sometimes you cannot test a large number of participants. If you have a rare group of patients, then you cannot test a large number of participants. Now, without going into too much detail, I just want to say there are equivalent tests for each of the ones we talked about today that do not rely on normal distribution. Those are so-called non-parametric tests. And they are based on different things. They're not based on normal distribution. Now, you would maybe think, why not always use them? Well, they have different problems again. So it's not like there is no perfect test. But in certain situations, they may be better. And those situations would be if the assumptions are not met. Now, I don't want to go into detail into any of those. That would be part of another lecture, but just to show you that there are alternatives. Now, another alternative that there is that you transform your data. Now, for example, in the lower part, you see that there is a skewed distribution, skewed to the right. And this is something that happens a lot, for example, when you look at reaction time data. Because in reaction time data, it often is the case that people are relatively quick, around 300 to 400 milliseconds, but then there are outliers to the right. So sometimes you just are not paying attention, and then all of a sudden your reaction time is a second. Or you are in doubt, and then you cannot make a decision, and it takes really long to make a decision. So reaction times in many tasks that we would use in psychology and neuroscience, they are typically not normally distributed. So you could take one of those other tests, but you can also transform your data. For example, you can take each reaction time score and take a log transform, so basically take the logarithm of each score. What that will do is, because the log values, the higher a value is, like the change in values if you do a log transform is different, because the log follows a certain curve. And then you would get a more normal distribution as well. And then you can do statistics on this log transform data. And you will see this in a lot of papers that use reaction time. You will see not reaction time, but log reaction time. That's why they do it, because they transform the data to use their ANOVAs or t-tests. Now, finally, I want to come back to these p-values, because I talk about them throughout this entire lecture. But I really want to reiterate this point, what this p-value is, because it sometimes is used in a way that is not really correct. So as I said, the p-value just reflects the probability that a given statistic or a given observation is based on chance level, right? So if your p-value is very small, then in your normal distribution it is very far to the right or very far to the left, which means that the chances of randomly picking a value within this normal distribution, the chances of that being very, very high or very, very low, that chance is very, very small. That's what a p-value represents. So if you have a p-value of 0.04, there's a 4% chance that you would find a group difference just on chance. So there's a 4% chance of that being just a random group difference. Now, if that value is so small, we typically say, okay, well, it's unlikely to be chance because it's only 4% chance. But if your p-value is 0.001, then there's only 0.1% chance that a certain group difference is based on it's just random. So what that means is that the p-value, how you interpret that, the p-value is basically just how certain you are that two groups are different. If the p-value is 4%, then you are certain, or to some extent certain, that there is a group difference, but there's still a 4% chance of this just being coincidence. Whereas if your p-value is 0.001, then you are even more certain, because the chances of this being a coincidence are just 0.1%. And if your p-value is 0.0000001, then the chance of that being a coincidence is almost non-existent. So a p-value is more a certainty measure, but it doesn't tell you so much about how large a difference actually is. Because how large a difference is, that really depends on the number of participants you test. Remember, when we calculated our t-values and our ANOVAs, we always divided by the degrees of freedom, which is the number of observations minus the number of groups. So if you have a lot of observations, then your t-value becomes higher and higher and higher, which means that your p-value becomes smaller and smaller and smaller. So a small p-value doesn't necessarily indicate that a difference is really big. So when you read a paper and they find a significant difference, that significant difference means that they are relatively certain that there is a difference, but it doesn't necessarily mean that it is a big difference. So, and this is something you see a lot in news articles when they talk about significant differences, that they make this mistake of saying something was really significant, so therefore there is a huge difference. Not necessarily the case. Because if your p-value is very, very small, 0.00001, but you also have a very large sample of 1,000 people, then that difference in effect could be a lot smaller than, for example, if you just have a p-value of 0.049, which is just barely significant, but you also only tested 20 participants. So in that, so it could be, for example, when you test 100,000 people, you test 100,000 coffee drinkers versus 100,000 tea drinkers. you might find a significant difference in IQ score. But if the IQ score of the coffee drinkers is 100 and the IQ score of the tea drinkers is 100.1, then yes, on so many people that may be a significant difference. But that difference is obviously almost meaningless, because a person with an IQ of 100.1 is not really smarter than a person with an IQ score of 100. So when looking at p-values, don't make the mistake to think this is a big effect or a small effect. It's just about the certainty you have about whether there is a difference or not. And it also just implies that it isn't always the best thing to just test a huge amount of participants. Now, sometimes it is. For example, if you would want to look at what are the side effects of a certain medication, right? Even if there is a very, very small effect, even if a side effect only occurs in a very small amount of people, we still would want to know. So if we would do that kind of research, we would want to test a lot of participants. But when, for example, looking at IQ score, as I said before, the difference between an IQ of 100 and a 100.1, that is not something that tells us anything about differences in intelligence. So when we're doing a test on IQ score, we don't need to have as many participants. And of course, given that science unfortunately costs a lot of money and doing tests costs a lot of money, it sometimes can be beneficial to test a fewer amount of people and then save that money to do just another test later on. That can be much more valuable than testing something in 100,000 people. So sometimes if you read news articles or see a video on YouTube where they say, well, this study only did it on 20 people and therefore it's useless, that's not the case. It really depends on what they measure. And if they did it on 20 people and they found a significant effect, then they are relatively certain that that effect is real, and that effect is probably quite large as well. So that might be even more interesting. So that's it. It was quite a long talk, and I hope you at least get something out of this. My intent was to more give like an idea of how to interpret statistics rather than to have the nitty-gritty of how to calculate everything. So with the idea of when you read an article that you know how to interpret that. So I hope you enjoyed this, and yeah, see you the next time. Bye-bye.